Again, welcome back to calculus. This lectures will continue with the functions and their graphs. Our main objective is to learn how to classify functions and also recognize combination of functions. Now, we know by the end of 18th century, mathematicians and also scientists have classified functions, which we call the elementary functions, into three categories. One is algebraic functions. Example will be the polynomial, radical, or rational. Also trigonometry functions such as sine, cosine, tangent, arcsine, etc. Then we also have the exponential and log functions. So the most common one is the polynomial functions. Normally in college algebra, we always start with polynomial functions first. So example of a polynomial function can be f at s equal to an x to the power n plus an minus 1, x to the power n minus 1, all the way plus a0. Now, n is a non-negative integer. So the numbers ai are the coefficients, with an the leading coefficient, and I'll say a0 will be the constant value. So example of a polynomial function can be a quadratic function. Let's say 3x squared plus 2x plus 6. So 6 will be the a0, it's a constant value. And also, if an is not equal to 0, then n is the degree of the polynomial function. So a quadratic equation, the degree of it is 2, because the highest exponent is 2, which in this case, the highest exponent will be n, because the next one is n minus 1 all the way to the constant value. So the zero polynomial function f at s equal to 0 is not assigned a degree. It's not assigned a degree. So it's very common practice to use a subscript notation for coefficient of a general polynomial functions. But for polynomial function of low degree, these simpler forms are often used. So for example, a 0 degree, we say f at s equal to a. A is a constant value, so it's a constant function. Or the first degree, as we said earlier, if the exponent, the variable, the exponent of the variable is 1, then we have a linear function. So f at x equal to ax plus b is a linear function. Then the second degree always will give us quadratic function, which example here, ax squared plus bs plus c. Again, a, b, c are constant values. So a and b are the coefficient of x squared and x. Then c is a constant value. Then we may have a third degree, which we call the cubic function, as cubed plus bs squared plus cs plus d. So this is very common. We use a lot in college algebra. So whether the graph of f at s equal to a n x to the power n plus a n minus 1, x to the power n minus 1, etc., eventually rises or falls can be determined by the function's degree, whether the degree is odd or even, and also by the leading coefficient, whether it's a positive or a negative also. So here, for example, we have a function here, up to the left and up to the right, and this is a polynomial function. Now, the curves here will depend on the number of degrees we have. So linear, there's exponent is 1, so a straight line. And this graph here, the exponent will be 2, polynomial or quadratic equation. So again, here we say an is greater than 0. Here an is less than 0, so it's open, polynomial open downward. If you open upward, then an will be greater than 0. Then here we have down to the left and also up to the right, an is greater than 0. And also up to the left and down to the right, it means an will be less than 0. Now, we should know that the dashed portions of the graph indicate that the leading coefficient test determine only the right or left behavior of the graph. So that's the only thing we should note on the dash section. So this is the idea of a classification and also combination of functions. Now, the next we have, just as a rational number can be written as a quotient of two integers, A rational function also can be written as a quotient of two polynomials. So example here, we have f at s equal to p at x over q at s. This is again a rational, this is also a rational function. So we say a rational function can be written as a quotient of two polynomials. So f at s equal to p at x divided by q at s, only if q at s is not equal to 0. So both p at x and q at s are polynomial functions. So polynomial functions and rational functions are examples of algebraic functions. So an algebraic function of x is one that can be expressed as a finite number of sums, differences, multiples, quotients, and also radicals involving x to the power n. So for example, f at s equal to x plus 1 all square is algebraic function. Also, functions that are not algebraic are transcendental. We will see an example of what is a transcendental function in a few lectures to come. So trigonometric functions are transcendental, which will be our, again, next lectures. So two functions can be combined in various ways to create a new function. For example, giving f at s equal to 2s minus 3 and g at s equal to s squared plus 1. So combination, we can do either addition, subtraction, multiplication, division. So we know f at x is 2s plus 3, g at s is s squared plus 1. So f plus g at x will give us 2s plus 3 plus s squared plus 1, which is what we have here. Or f minus g at x will give us f at x minus g at x, which will give us 2s minus 3 minus s squared plus 3. Or we may have f g at x, which is f at s times g at x, which will give us 2s minus 3 times s squared plus 1. Then the quotient also will be f divided by g at x, which will give us f at x divided by g at s, which is, so those are the possible combination, arithmetic operation of functions. So here we say you can combine two functions in yet another way called a composition. And we may discuss this later, what is a composite functions. So that's the definition of a composite function. So we have a function f and g. So we can have a composite function of f and g, which means the function f will take the argument of g function. So f composite g at x is f at g at x. So now g at x, a function, is an argument of the function of f at x. We can have it the other way also. So if we have a composite g and f, then it will be g at f at x. So now f at x is the argument of g at x. Again, we will see example. So let's see some few examples here. Here we have a function f at x equal to 2s minus 3. We also have g at s equal to s squared plus 1. Find each composite. So we're looking for f composite g. This means I'll write down the f at x, which is 2s minus 3. Anywhere I see x, I'm going to replace it with s squared plus 1, which is g at x. Because now g at s is the argument of f at x. So let's see how they solve it. So here you can see how we wrote it. F composite g at x is f at g at x. So I write down s squared plus 1, which is what? The g at x. Now what is f? F is 2s minus 3. So our solution will be, anywhere I see x in f at s, I will substitute it with s squared plus 1. So we get 2 s squared plus 1 minus 3. Why? Because f at x is 2x minus 3. So anywhere I see x, I'm going to substitute with g at x, because g at x is the argument of f at x. So here we solve it and we get 2s squared plus 2 minus 3, which will give us 2 minus 3 will give us minus 1. So our final solution will be 2s squared minus 1. Now let's do the opposite. G composite f, which means anywhere I see x squared, I'm going to replace it with 2s minus 3. Because this time f at x is the argument of g at x. So we write it in this form. And we can see now we wrote down the f at s, which is 2s plus 3. So anywhere I see the g function, anywhere I see x, I'm going to replace it with 2s plus 3. And that's what we have here. So we have s squared plus 1. So it will be 2s minus 3 squared plus 1. And that gives us 4s minus 12s plus 10. Now we should note that f composite g at x is not equal to g composite f at s. As we can see the answer here, this gives us 4s squared minus 12s plus 3 plus 10. And the previous one gave us 2s squared minus 1, which is f composite g at x. So an x-intercept of a graph was defined to be a point where x can be any value, but y is 0. And also we saw the opposite. Y-intercept means when s is 0, what's the value of y? So s-intercept means when y is 0, what is the value of x? So in other words, the zeros of a function f are the solution of equation f at s equal to 0. So for example, f at s equal to s minus 4, we can say, okay, has a 0 at s equal to 0, equal to 4, because if I say s minus 4 equal to 0, s will give me what? Plus 4 plus 0, which will be, again. So that's the whole concept, and we will see an example soon. So in the terminology of functions, a function y equal to f at x is even when its graph is symmetric with respect to the y-axis, and also to be odd when the graph is symmetric with respect to the origin. So the symmetry test can give us the following test for even and odd numbers. So a function y equal to f at s is even when f at negative x equal to f at x. A function y equal to f at s is odd when f at negative s is equal to negative f at x. So always we can check if a function is even or odd functions. And that's the two conditions here. If I have f at negative x is equal to f at x, then it's even. Then f at s is even. So let's see an example. They say we should determine whether each function is even, odd, or even neither is possible. So find the zeros of the function. So here we are going to write down f at s equal to s cubed minus x. So I'm going to see if I'll get the same s cubed minus x if I replace x with negative x. So f at negative x will give me negative x cubed minus negative x, which give me still negative x plus x, which if I take the negative out, I'll get x cubed minus x. And s cubed minus x is what I have here. So I have negative f at x. So this means f at x equal to negative f at s. So this function is a odd. Remember the rule said, if f negative x, if I have f at x and I replace x with negative x and I still get the same f at x, then it's even. But if I replace it with negative s and I get negative f at x, then it's odd. If none of them, then it's neither. So that's why here we get odd, because we replace x with negative x. So we get negative s cubed minus negative x. Negative s cubed, anytime s raised negative value raised to an odd exponent, you get negative. If it's raised to an even exponent, you get positive. So here we get negative x cubed. Negative times negative here give me plus. So now I'll take the negative out and see if I get the same thing. And I got s cubed minus x. So this is odd. Now let's look at the second question. So the second one, let's see. We have actually, let's finish with the first one. So the zeros of f are s cubed minus s equal to 0. We can factorize x squared minus 1. This is difference of 2 squared, s squared minus 1 will give me s minus 1 times s plus 1. So this means we get x equal to either 0 or 1 or negative 1, because first s is 0 S plus 1 equal to 0 will give me S equal to negative 1. S minus 1 equal to 0 will give me S equal to positive 1. So these are all the zeros of the function. If S is 0, 1, or negative 1, we get 0. So this is how the graph looks like. So you can see, because we have 0, 1, negative 1, you see we get our plots, our 3 points on the x-axis, because y is 0, so x-axis. And then we come with the graph. Now let's look at the b. So the b, we just substitute the function. Let's look at the function already. So the function is just g at x equal to 1 over x squared. So we just substitute with the negative value. So let's look at it again. So we get negative x. So this means we get 1 over negative x squared. Now we know negative x, if it's even number, it will still give us positive. So this means g at x value is the same as g at negative x value, which will give me g at x. So this is even number, even. Now we can also, this function does not have any zeros because 1 over x squared is positive for all x in the domain. Now let's look at the c. C, again, we have our function to be, I think, negative x. Looking here, let's go to the function. So c will give a negative x squared minus x minus 1. So anywhere we see x, we substitute negative x and test it and see. So x become negative x here also. So negative x squared will give me positive. So this will change to negative for me. Negative times negative is positive, and then we have negative 1. So here, because h at x is negative x squared minus s minus 1, and negative h at x should give me s squared plus s plus 1. So this will conclude that it's neither odd or even, because we are getting different answer altogether. The original is negative s squared minus s minus 1. When we place it to negative, we shall get s squared plus s plus 1 if we multiply everything by negative 1. But we get negative s squared plus s negative 1, which is not the same as the h at x, and also it's not the same as negative h at x. So this means it's neither even or odd function. So here we say function is not a odd and function is not even. So the function is neither even or odd. So this function does not have any zeros because negative x squared, negative x is negative for all x, as we can see on the graph. If we plot the graph, we get something like this. So this will be the conclusion of our lecture. So the main goal of this lectures again is to classify functions and also recognize combination functions. Combination functions, as we said earlier, can be arithmetic operations such as plus, minus, quotient, and multiplication. And also we saw the concept of composite function, where one function can be the argument of another function. So again, wish everybody the best and see you in the next lectures.